I'm lying. My lips are moving. Right? Why not? What's the point of telling a good story if you can't stretch the truth a little bit? Okay, Tom, let's pick on you. So, Tom is in the desert. The Kalahari. Tom is in the Kalahari, and he's here having a bad day because he has a broken leg. There's Tom's broken leg. You were the defective baby? It's tough, man. It's tough. So this is just prior to throwing you off the cliff, Jacob. Yeah, now's a good time. You got to watch this later on. So, anyway, the good news is Tom has a little bucket. That is attached to a rope. And he has the ability, Rob, he has the ability to, and there is water. There is, well, no, he can't make it off the, he can't make it off the cliff. The water's not that deep. He might break his other leg. Okay. So, the bad news is the bucket has a hole in it. No. Okay? So that's the scenario. Now, let's talk about all the, let's talk about this crazy scenario here. And the big question is, how much work is required to raise a bucket of water 20 meters if the bucket leaks at a constant rate of change and becomes empty at 20 meters. Yeah, it is. So Tom lowers the rope, fills the bucket, raises it up, and it's leaking, and just as it gets to the top, it's empty. That's his personal hell. No, this is more fun. This is more fun. Well, we may look at that too. It's in the desert. It's in the desert. Tom's having a bad day. Okay. So, this is a perfect type of calculus problem because what all is going on in terms of work? Okay, he pulls on the rope. Now, as the rope gets shorter, what happens to the amount of work that gets done? It decreases. Why? Because the mass of the rope decreases. The rope weighs a certain amount per meter. Yeah? No. Hang on. We're not talking about water yet. We're just talking about the rope. Okay? As you pull the rope up, salud. As you pull the rope up, the amount of work needed to pull it up gets less. Agreed? Okay. Because part of the rope is spooled up beside his pathetic broken leg. Okay, now, what else is happening? Okay, so at the bottom here, the bucket is full of water. And then what happens is in terms of work? Right, there's less water in the bucket, and so the amount of effort it takes is gradually less and less and less. Okay? Good. What other consideration do we have to do to solve this problem? The rope has mass. Gravity will come to play here. That's true. The rope has mass. The water has mass. The bucket alone, because there's a certain amount of work that's going to be needed just to pull the bucket up. And how does that work change? Why? Right. The mass of the bucket is constant the whole time. Okay. Good. Now, looking at these things together, this is like a crazy problem. But you can break it into parts, and then it's going to be okay. So what are the parts, Mo? What's that? Oh, I'll give you that. I'll give you that. I think I can't remember what I had. I pulled this from somewhere. Don't worry about that for right now. Just in general. In general, what are the different components of this job? Okay, work done what? Doing what? The work done. Okay, lifting the bucket. That'll work. Bucket alone, we'll say. Okay? B, how about that? Work done lifting the water, the rope actually doesn't matter. The water, and the key here is alone. Along. The water alone. Break it into its individual components, and then it's not so bad. Lastly, the work done lifting the rope. Okay? Alone. And then part D, we can add them all together, take the sum. Okay? And if we break it into those parts, life's good. So, let's talk about this. What do we say first? Bucket. Bucket alone. All right. And did I have a volume on the bucket? I need to find one then. Oh, okay. So bucket alone weighs 22 newtons empty. Now, this is a biggie. No kilograms because we want to do everything in terms of newtons. It'll make our lives much, much, much easier. Okay, right. But a bucket of water exerts a force, does it not? Okay. So let's take a moment out and talk about units. 1 Newton, you physicists. 1 Newton equals what? It's not over. It's 1 kilogram. It's the acceleration needed to raise 1 kilogram 1 meter per second squared. Yeah. Okay. And that's important. And then work. How do we measure work? Work is measured in what units is that though? Joules. Okay, joules. And what's a joule? Somebody other than Trevor. Getting ordained in calculus. All right, somebody other than Trevor, stay with it. Colton, what's a joule? It is a unit. It's a unit for measuring how much work is done. Yes, Newton meter. Newton meter, and it is force times distance. Very good. Okay. And I know you all have had this in physics, but we're trying to combine physics and calculus, which is really, really what calculus is great for. Okay. So the bucket alone weighs 22 newtons empty with nothing in it. All right? So we can say that the 22 newtons exerts a constant force for 20 meters. So the work equals 22 newtons times 20 meters. So the work equals 440 Newton meters equals 440 joules. Okay, you can also think of this graphically. You know, pretty much everything can be thought of as a rectangle. Not everything, but a lot. 22 newtons, 20 meters. The work done graphically can be thought of as the area of a rectangle. 440 Newton meters, which are joules. Okay, any worries on that? Jeremy, you're a physics guy. How much of this stuff have you had in physics? So kind of connected. And who in here has not taken physics? Okay, a couple of you. All right. So what I would really, really strongly suggest is at Colgate next year and at George Fox next year, Colton, take a calculus-based physics course. Trevor, you say that, but you took it in the fall and got your butt kicked, and then what did you do? And then what did you do? So is that a masochist? One who enjoys having others inflict pain upon them? Yes.
No, it's actually pretty fun.
I just feel like I feel like, Jeremy, there's no point in taking calculus without physics. There's no point in taking physics without calculus at some point. I mean, I think what you get here is good. It's a good, theoretical foundation. But man, once you start taking it with the calculus, things pop and snapple and crack. Yeah. Okay. Now, so we've got the bucket alone. Mo? Yeah. So this will be online tonight, Mo, if you're gone for a long time. Okay. We've got the bucket alone. Okay, so B. What did we say was B? I can't remember. Water? Water alone. Okay, that part's not too bad. So water alone, well, let's think about this. Force needed to lift the water is what, Johnny? Decreases because of the leak. Right. With respect to distance. I like the way you said that. You're starting to talk like a math dude. With respect to distance. Okay, so once again, we can say, maybe I'll do another drawing over here. Okay, so Tom's up here at 20. Tom. The water's down here, water source. Okay, so at any point on here, what's the distance from here to here? We can call this x, right? Or would we be better off? I'm trying to think of the best way to do that. At any point, no, let's call it 20 minus x. Let's call it 20, that's easier. 20 minus x, call that one x. Okay? At any height here, it's just going to be 20 minus x, so we can do that. Any worries there? So it's groovy. And the water source is down here. Well, we're going to call this 0, and we're going to call this 20, so at any point here, it's 20 minus x, right? Yeah. Okay, decreases. Now, we got to talk about newtons. Okay, how do I say that? 1 liter of water weighs how much? Yeah, you do. It is a kilogram. I mean, the metric system is so beautiful in this regard. It's perfect. And actually, if you want to get geeky, it's 1 liter of water that's clear water, no salt, at sea level is 1 kilogram. But that's okay. Close enough. Right. Okay, so acceleration due to gravity is how much? 9.81 meters per second squared. Again, depending on where you're standing. The Earth's an oblate spheroid, and it changes a little bit. Acceleration due to gravity is 9.81 meters per second squared. Okay? So we can say that, were we given anything? I got to remember that. I can't remember what all they gave us. Just a sec. Okay. So we were given 70 newtons of force in full bucket from the water, okay? So if you're curious, you can say 70 newtons divided by 9.81. And what are newtons? There you go. Kilogram meters per second squared. Grace, it's going to be a few minutes, so relax. You can hang. Yeah, that'll be fine. That'll be fine. Kilograms meters per second squared. What is acceleration due to gravity? Meters per second squared equals, what's 70 divided by 9.81? Okay, 7.1, close enough. Units? Kilograms equals, so how many liters? 7.1 liters, okay? If you're curious how big the bucket is, okay? A liter's like a quart, so that's almost 2 gallons. That's a liter, so 7 of those. Not pretty normal bucket. Okay, so some of this stuff was given, but I just want you to have some sense with reality, okay? So about 7 liters in the bucket, 7.1, 70 newtons of force when the bucket's full, okay? So down here, then, we're 70 newtons to lift it. And what about up here when we get to Tom? 0 newtons of water because it's empty. Poor guy. You'll just see him. He'll be going like trying to lick the side of the bucket because he's hurting. Okay, so we're going from 0 up the top or from 70 at the bottom to 0 newtons at the top. Work done lifting the water alone. Okay, so let's see if we can write that into some kind of function f of x, with x being distance. So we could say that that's 70 newtons times, what happens with distance? So we need some kind of a proportionate type thing. Yeah, that kind of a deal. We can say it's 20 minus x over 20 at any point then. This is a function that can model the amount of force at any distance x. Well, let's test it. I like that, Johnny. I like that. Test. So let's say you're halfway up, right? 70 newtons times 20 minus 10 over 20. That's half. And will it give us half force? 35. Okay, what about if you're like a third of the way up? 20 minus 20 thirds over 20. Does that work? Because, well, a little bit messy, but when you're a third of the way up, you would expect to have, what, 2/3 of the force remaining? Which will work, because this will be like 14-ish over 20. So, that works. That's good. And a good point, Johnny. Okay, so we're doing good. We're doing good. So, and you may want to clean this up a little bit. You don't have to. Yeah, I think you could do that. I haven't looked at that specifically. You could write this as 1 minus x over 20 and distribute it if you wanted to. Okay, let's do that. 70 minus 7 halves, or 3.5 for you decimal freaks. Doesn't matter. You liked it better before? Well, this will be nice and easy to integrate because it's linear. And remember, when we can, we want this to look clean before we integrate. And then try to find some table that fits. Make it clean first. Okay, so then the work done would be the sum of all this, right? Over the entire interval from 0 to 20, would it not? Jeremy, that is the biggest, ugliest yawn ever. You're going to cause me pain. Breathe. You're not getting enough oxygen. Is that it? His brain's overheating? It could be. All right, here we go. So the work done then would be the sum of all the little instantaneous works done at any x. Yeah, I like that. I'm going to invent a new word, a Bushism. Okay, of f of x dx. It would be the sum of all of that. Okay? Now, think about units here. That's a W for work. What units is my function in? newtons, what units is dx in? Meters. So when you go newtons times meters, you get newton meters or joules. And it's important for you to just be aware of these units and how it works out. You're summing all of these into one cohesive work over this interval. Okay, so we've got work from where to where? 0 to 20 of 70 minus 3.5x dx. 20. Thank you, Jeremy. Yeah. Well, sometimes if I don't press hard enough, at the time I actually wrote the 0 and it just didn't collect. So I got in a hurry. Okay, w equals 0 to 20, the integral of 70 minus 3.5x dx. Okay, you know what to do now. 70x, 7, here I keep doing it. 70, what's that? Okay, we can do that. Fractions are friends. Is that okay? It should be like that. How about? That should work. Evaluated from 0 to 20. So W equals 70 times 20 minus 7/4 times 20 squared minus 70 times 0 minus 7/4 times 0 squared. I know that seems silly, but don't forget. I mean, so many people just get used to saying, oh, the rest is 0. You know, and then there'll be a signed 0 in there somewhere. Or there'll be e to the 0. Exactly, Johnny. And they'll just say, oh, it's just 0. It's gone. So be careful. So W equals, what is this? 1,400 minus 2,800 over 4. Oh, that comes out nice. Equals, is that 700? Newton meters equals 700 joules. Ha ha ha. Okay, we're doing good. We're doing good, Tom. There's hope. There's hope. Okay, so then we got the rope alone. And this maybe is my favorite part, Mo. This is maybe my favorite part because we think of that 1 meter of rope. And did they give us something on that? Just a second. Oh, there it is. Okay. Similar. Let's check it out. So we're going to say C, rope alone. Rope alone weighs 0.4 newtons per meter. Okay, so that means 1 meter of rope is 0.4 newtons per meter. And again, we're not thinking of this in terms of kilograms. We're thinking of it in terms of the force that the rope exerts. Okay? Or the force needed to lift the rope. Think of it like that. All right. So, man, this is crazy. What are we going to do with rope? Skip a rope. Right, so we could say the force at the top is 0, and the force down at the bottom, okay, at the bottom, what's it going to be at the bottom? Alex, 0.4 what? You started out? Times what? Times 20 units meters. Okay? Yeah, so I believe he's okay. Equals 8 newtons, because the meters are going to divide out. Oh, yeah, that's right. And then at the top, what's it going to be? 0.4 newtons per meter times 0 meters equals 0 newtons. Okay? And then anywhere in between, what's it going to be? -20 x, because remember, this has to change as the distance changes. Okay? That's the important thing. Well done. So we can say then the integral from 0 to 20 of what? Alex, you're on a roll. You might as well keep going. Mm-hmm. I'd multiply it in 20 minus x. Correct. It's not changing. Great. It's not changing, so then we can just say dx. Good point.
Instead of the starting thing is the rate of the change, whereas before it was the total force minus the rate.
Correct. So this one's a little bit different. And that's one thing I like about this problem a lot, Mo, is that it takes 3 different scenarios. And this will be available. I know Trevor's distracting you, so you should probably watch this tonight. Okay? Watch this tonight. Okay? All right. So then we're almost done, and this is cool. This is cool. So then we've got the work equals, let's try to clean it up before we integrate. 0 to 20. What do you got? 8. We did 8 already. 2/5 x dx. Okay. And that's not bad. Again, linear. So we can do it. The work equals, what do we got? Come on. 8x over 1, if you want to get geeky, minus 2/10 x squared. Not anymore. Evaluated from 0 to 20. The work equals 8 times 20 minus 1/5 times 20 squared minus 8 times 0 minus 1/5 times 0 squared. Work equals, what is that, 160 minus, that's 400 divided by 5, 80. The work equals 80 joules. Okay, so if we put them all together, total futile effort, work exerted by sad life Tom is, so what did we have? What was our first one? I can't even remember. We had 440 joules. Oh, poo. Thank you, Jeremy. It should be 440. 440 joules plus, what was the second one? 700 joules plus 80 joules. It kind of does. I never noticed that. That's funny. Okay, equals 1,220 joules. Tom's very strong, and he gets nothing out of it. There might be a little bit there. All right. Questions?